Ever wonder how massive, complex software gets built without becoming a tangled, unmanageable mess? Well, the secret isn't just about writing more code, it's about writing smarter code. Today, we're going to unpack two fundamental principles that let developers build programs that are efficient, reusable, and, really importantly, secure.
So, let's put ourselves in the shoes of a programmer. You start out by modeling a real-world object. Let's say a dog. You create a dog class, which is basically a blueprint for all the dogs in your program. Easy enough, right?
Okay, but then your project starts to grow. Now you need a cat class, and then after that, a horse class. You start coding each one from scratch, and pretty soon you're getting that feeling of déjà vu. You realize you're writing the same basic behaviors over and over and over again. They all eat, they all sleep, they all move. I mean, you're sensing a pattern here, right? Because your keyboard definitely is.
So yeah, that feeling? It's not just in your head. It points to a really fundamental problem in software development: code duplication.
I mean, if you think about it, without a better way, you'd be writing an eat method inside your dog class, and then turning around and writing the exact same eat method inside your cat class. Now imagine you need to change how eating works. You'd have to go find and update it in every single animal class you made. That's not just a huge pain, it's a recipe for bugs.
Well, thankfully, there's an incredibly elegant solution to this copy and paste nightmare. It's a concept called inheritance. So instead of thinking about each class as its own separate island, we can see they all share some common features. Inheritance lets us group all these shared traits and behaviors into a more general, higher-level category we can just call animal.
What this does is create this really powerful logical connection we call the is-a relationship. A dog is a type of animal. A cat is a type of animal. See how that works? The more specific classes, which we call subclasses, are derived from the more general superclass.
Now, it's super important to separate this from another common relationship you'll see in programming: has-a. For example, a triangle is a shape, so inheritance makes perfect sense there. But a vehicle has an engine. The engine is a component of the vehicle, not a type of vehicle. That's a whole different design approach, right?
All right, so let's see what this actually looks like in the code, because that's where the magic really happens. Okay, first up, we create our parent blueprint, the animal class. We put all the shared stuff in here, like a weight variable and that eat method we keep talking about. This becomes our single source of truth. And now check this out. For our dog class, it's incredibly simple. We just use one single keyword, extends. By just saying dog extends animal, we instantly give the dog class all the properties and all the methods of the animal class without writing any of that code ourselves.
So what that means is, in our main program, we can create a new dog object and simply tell it to eat by calling the dog.eat method.
But wait a minute. If you look back at our dog class, it's basically empty. We never actually wrote an eat method for it.
So how in the world does the program know what to do? The answer is, it works because the dog class inherited it from the animal class. And this right here brilliantly illustrates the core advantages. We've completely gotten rid of duplicate code. And if we ever need to change how all the animals eat, we only have to modify it in one single place, the animal class, and bam, that change is automatically reflected everywhere.
Okay, so we've solved the efficiency problem, which is awesome. But this solution kind of introduces a new, more subtle challenge: data security. Right now, our code is maybe a little too trusting.
Let's go back and look at our animal class for a second. See that word public right next to the weight variable? That means that any part of the program, from anywhere, can directly reach in and change an animal's weight. Someone could accidentally set it to like a negative number, which makes 0 sense and could totally crash our program.
So, we need a way to protect our data from being misused. And for that, we turn to another core principle: encapsulation. You can think of it like building a protective vault around your class's most important information.
So what is encapsulation? Really, at its heart, it's all about bundling the data, like our weight variable, and the methods that work on that data, like an eat method, together into a single self-contained unit. The class itself becomes a protective shell. And we do this what's often called data hiding with a pretty simple two-step process. First, we stop giving everyone direct access by marking our variables as private. Then second, we provide controlled access through special public methods, often called getters and setters, that act as the official gatekeepers to that data.
This access table really shows the difference. Public, at the top, is a total free-for-all. Anyone can access it. But private, way down at the bottom, that's the ultimate lockdown. Access is only granted from within the exact same class. Nowhere else. Period.
And this, right here, this gets to the core of why we do this. It's all about preventing misuse. You're essentially creating a black box. Other programmers can use your class, but they can't see or mess with its internal logic. They have to go through the proper channels you've set up, which makes sure the data always stays valid and consistent.
So, when you put it all together, we have these two incredibly powerful ideas. Inheritance lets us reuse code and build things really efficiently, while encapsulation protects that code from falling apart. This brings us to a final thought. How does this fundamental balance of reuse and protection make massive, mind-bogglingly complex software, like the operating system on your phone, even possible in the first place?